Look at a thunderstorm, and you are watching raw electrical power rip through the atmosphere. But the exact same mechanics driving that massive discharge are at work when you pull a synthetic sweater over your head and hear it crackle, or when you touch a doorknob and get a sudden shock. To understand this force, we have to look past the human scale, down into a subatomic vacuum, where the base rules of these interactions are written. Let's isolate just two charged particles. The first qualitative rule of electrostatics is straightforward. Objects carrying the exact same charge polarity violently repel each other. Conversely, objects with opposite charge polarities are drawn together. The strength of this push or pull is dictated by the magnitude of the charges themselves. A larger concentration of charge generates a proportionally stronger interaction. Knowing that likes repel and opposites attract is a useful physical observation, but it is entirely insufficient for physics. To predict behavior, we need a precise mathematical framework. The true governor of electric power is distance. As these particles move apart, the strength of the force doesn't drop linearly. If you double the distance separating them, the force shrinks to exactly 1/4 of its original size. This specific geometric relationship is called an inverse square law. It means the force is inversely proportional to the square of the distance. Bring the charges closer, and the force surges based on that same ratio. Halving the distance results in a 4-fold increase in strength. Our ultimate mathematical model must accurately calculate this exact force magnitude based on the distance. Then comes the second requirement, calculating the precise three-dimensional direction in which that force acts. We must build a single equation that seamlessly calculates both magnitude and direction without breaking. And to do that, we look back to the fundamental experiments that first proved these relationships. The study of static charge began around 600 BC, when the Greeks observed that rubbing amber with wool caused it to attract light objects. In fact, the word electricity is derived from the Greek word for amber, electron. By the late 18th century, physicists needed a way to measure these invisible forces with strict precision. The French physicist Charles-Augustin de Coulomb solved this problem with a highly sensitive device called a torsion balance. This diagram illustrates the mechanism of the torsion balance. It works by suspending a charged metallic sphere on a delicate vertical wire. When a second charged sphere is introduced, their electrical interaction causes the wire to twist. The degree of that twist accurately measures the physical force between them. Coulomb varied the separation distance between the charged spheres and carefully recorded the changing twist angle of the wire. By comparing forces at different distances, Coulomb proved the inverse square relationship. He achieved this without even knowing the absolute mathematical value of the charges on the spheres. This physical device provided the raw historical data necessary to write the first draft of the mathematical formula. That first draft is Coulomb's law in its scalar form. Looking at the right side of the equation, Q1 and Q2 represent the specific magnitudes of the two interacting point charges. The denominator, r², represents the distance separating them, explicitly defining the inverse square law demonstrated by the torsion balance. Then we have the constant term at the front of the equation, 1/4 pi epsilon naught. The symbol epsilon naught is a specific physical constant, known as the permittivity of free space. Permittivity defines the baseline resistance of a vacuum to the formation of an electric field. It tells us exactly how easily electric force can permeate empty space. This equation accurately measures the push or pull between particles, but it has one limitation. It only provides the raw, scalar strength of the force. Because charged objects exist and move in a three-dimensional universe, a purely scalar equation leaves us blind to where the particles are actually going. We must upgrade the math to vector geometry. Mapping direction requires a strict spatial framework. We start with a standard three-dimensional coordinate grid with a defined origin point. Now we place two generic point charges, Q1 and Q2, floating within this space. To define their absolute locations, we draw position vectors, R1 and R2, pointing directly from the origin to each individual charge. We know that electrostatic force acts centrally, meaning it only travels along the straight, direct path connecting the two particles. We define this path by drawing a separation vector between them. The vector leading from charge 1 to charge 2 is denoted as r21. To isolate the concept of direction from the actual distance between the particles, we use a mathematical tool called a unit vector. The unit vector, written as r21, has a magnitude of exactly 1. It doesn't alter the strength of the force. It serves exclusively as a mathematical compass pointing along the separation line. With the absolute positions defined on the grid and a unit vector acting as our directional compass, the geometric scaffold is complete and ready to support the final equation. This gives us the complete model, Coulomb's law in vector notation. The elegance of this formula lies in its efficiency. We do not need to write separate equations to calculate attraction and repulsion. If we evaluate the force between two positive charges, the product of Q1 and Q2 results in a positive coefficient. Since the math evaluates to a positive number, the force vector aligns exactly with the unit vector, mathematically plotting the physical repulsion. But swap one charge to a negative polarity, and the product of Q1 and Q2 becomes a negative number. Multiplying the unit vector by a negative coefficient instantly flips its direction by 180 degrees, redirecting the calculated force inward to map the physical attraction. The inherent algebraic signs of the charges act as an automatic toggle switch for direction, making the equation universally applicable for any pair of charges. Applying Coulomb's law to more complex systems, there are three core properties you must remember. First, it is strictly an inverse square law. The resulting force is highly sensitive to the distance separating the two objects. Second, the force acts centrally. It will always travel strictly along the direct straight line joining the 2 point charges. Third, its vector form handles polarity algebraically, using the native plus and minus signs of the charges to dictate spatial direction. Coulomb's law provides the foundational mathematical bridge, translating the chaotic physical reality of a static spark into the predictable, rigorously structured laws of physics.